Welcome to the exercises for Chapter 7. Let's begin with exercise 1. Here is another one of these exercises where the goal is basically to write code that will implement a visualization in a figure. So figure 7.8. And in particular, this is focused on the iterative Z-score outlier removal algorithm. Quite a mouthful there. So let me go to figure 8 here, and then I'll explain what the figure shows, and then I'll switch to Python. So here we are in figure 8. So the idea here is to have a data cleaning method that's based on Z-scores and eliminating outliers that are identified through large Z-scores, but then have it iterative. So the idea is that you start with some data, and then you can see with the blue zeros. So this is the original raw data set, all the blue markers, including the X here. I'll talk about that in a minute. And well, one thing I did with this data set is force the values so that there are at least a couple of outliers, because it's not very interesting to write code for an outlier removal method if there are no outliers. So create a data set with 30 values that has at least one outlier, maybe a couple of outliers, and I'll let you figure out some way to create those outliers. And then the idea is you go through the data set once and you remove any data values that are excessive, that have a Z-score greater than some threshold. Now, for this illustration, I used a fairly lenient threshold of 2. Normally, that is too lenient to be really practical, but I used such a lenient threshold here just to illustrate the method. In practice, typical Z-score values are around 3, closer to 3. Yeah, so anyway, so here I said it's 2. So then whatever goes above the threshold is identified as an outlier, and that is this data value over here. That is Z-score of almost 4. Now, once you remove that outlier, then you recompute the Z-score. Now, the Z-scores will not be the same with and without this outlier, right? Because once you remove this outlier, you've changed the data set. So the raw numerical values are the same, of course, but the Z-transformed data values will have a different mean and a different standard deviation. And that's what you see in the red number ones here. So that is the Z-score in the second iteration. And there, this data point, which was this data point originally, now it moved up. It got further away because the standard deviation was smaller after moving this on the first iteration. Or maybe I should call it the 0th iteration. So then in the first iteration, or iteration 1, which is the second iteration, it gets confusing with these Python starting to count as 0. On iteration 1, which is the second iteration, this data point here actually shifted here and it became supra threshold. So it went above the threshold. And then it stopped there because the next time I computed the Z-score of this data set, there were no more outliers. So that's why you don't see any number 2s in here. Okay, so this is the figure. So you have to implement this iterative Z-score method and then produce this figure. If you're struggling with getting the 0s and 1s and X's, then don't worry about that. That is not the important part of this exercise. The important part of this exercise is to write the code to implement the iterative Z-score method. So here is how I simulate the data. You can see I start with 30 normally distributed random numbers. And then for no particularly good reason, I decided to have this simulation be limited to positive valued outliers. So therefore I say any small data values, so any data values less than -1 are shifted up by 2. Again, it's arbitrary. It's not important for the method. I just decided to do that, just basically to have all the outliers be positive and not negative. Here is where I added a bit of extra code to create some additional outliers. So I say that any data values above 1.5 get squared. So it's just a way of shifting up some of the larger data values, making them a little bit more extreme. Okay, so here I compute the Z-score. I stored this as a separate variable. As I mentioned earlier in the video, this Z-score threshold of 2 is pretty lenient. I would not recommend using that for most applications, but it just highlights the method really well here. Okay, now I have a for loop now, or a while loop. Now this while loop is, it never breaks, right? So it gets broken down here when there's no more data to remove. I'll talk about this more in a moment. So that means that we don't specify a set number of iterations to go through a priori. The method just keeps running until it has satisfied some criteria. Okay, so here we convert the data to z-score. Now you might think that this is, or you might think, let me scroll up, you might think that this line is unnecessary because I just compute the z-score again immediately in this while loop. But you can see I'm using the same variable, and that's because I want to use the same data z variable over and over again, removing the data value. So in fact, I do need this line of code up here, just in case you were curious. Okay, so yeah, you can also see I'm using NaN mean instead of just regular mean. And this is used to ignore NaN values. So if you have NaNs in the data set, then you can use NaN mean, NaN STD, and that will compute the mean and standard deviation, ignoring the NaN values. Otherwise, if you would have NaN values and you just use mean, then the result of this is going to be NaN, not a number. Okay, so then here, this is pretty straightforward. I find the data values to remove. And now here, this is not actually removing any data values. It's just identifying the indices. Actually, this is going to be a Boolean vector here. It's going to be all falses and trues. And wherever the z-score value is above the threshold, it's going to have a value of true. Now, if there are all values equaling false here, so if there's nothing true in this statement here, in this variable here, then the sum of that entire variable is going to be 0. That means there's no data to remove, and that's how we break out. Okay, that's how we end the for loop. That's the end of the iterative z-score threshold method. Okay, so here I do some plotting. I just say the data, the location, the index, the data index that I want to remove with a little bit of an offset, just so the visual indicators are not all overlapping on top of each other, and then the z-score values. Okay, and then here is a key line. I set this to NaN. So all of the data values that are marked for removal are set. Those data values get replaced with NaN. Now notice here that I'm not actually changing the raw data. So nowhere in this while loop am I changing the raw data values. So that's good because data z gets replaced with NaNs. It changes at every iteration, but we want to preserve the raw data and just know which data values we need to remove. Okay, and that's basically it. Then I update this num iters, count a number of iterations, and let's run this and see what it looks like. Now, because these are random numbers, every time you rerun it, it's going to look slightly different. So you see, again, the zeros are for the first iteration or iteration number 0, and there's already one outlier up here. Now, this is an interesting case, remarkably enough, just like the example I showed in the book figure. This data point here, data index 22 or whatever number this is, this was not identified as an outlier in the first iteration because it was below the threshold, because this value here was both pulling up the mean and also pulling up the standard deviation. And then when we remove this data value here after the first iteration, then the mean and the standard deviation changed. So then this data point here transformed into this data point. It got a bit further away from the mean because the standard deviation became smaller, right? And the standard deviation is the denominator of the z-score transformation. So when this value gets smaller, then these data points get further away from the mean, further away from 0. Now, just to show you what this variable looks like, data z, you can see there's two NaN values. So if you were using this method in practice, you basically ignore all of these values. You don't care about these. And you find the indices where there are NaNs, and those are the data values, or those are the indices that you would remove from the original raw data. Welcome to exercise 2 of chapter 7. This exercise and also the next exercise focus on a data cleaning method called trimming, data trimming. The idea of data trimming is that you just cut data points from the distribution, the top of the distribution and or the bottom of the distribution. You can remove a certain percentage of the distribution, or you can remove a certain number of data points. Now, this footnote here, 3, is stating that I'm actually not a huge fan of data trimming in practice. I generally don't recommend, I'm sure there's always going to be cases where data trimming is great and appropriate and valid, but in general, I don't recommend doing data trimming. But it does provide a really great opportunity to code, to make some exercises, to gain more experience with coding in Python, with statistics, working with data sets, distributions, and so on. So therefore, I have these 2 exercises that are using data trimming as a way to basically just improve your general knowledge about working with data and code. Okay, so that disclaimer out of the way. Start by creating a data set of 10,000 numbers defined as e to the sign of x, where x is normally distributed numbers. Couple of interesting properties about simulating data like this, e to the sign x. One is that, so just the sign of random numbers is pretty interesting. You get like a noisy sine wave, fluctuation that goes up and down. As you know, e to the anything is a strictly positive result. So this just is an interesting opportunity to explore the impact of trimming on mean and median, when trimming is appropriate, and so on. Okay, so then after creating the data, trim 4% of the data. So 2% from the lower tail and 2% from the bottom tail. And then I want you to replace the rejected data with NANs instead of removing those data points. So that means that your resulting post-trim data set will still contain 10,000 elements. If you set it up as a NumPy array, for example, there's still going to be 10,000 elements in that NumPy array, but 4% or 400 of those elements will be NANs, so you should count that 9,600 are valid. Those are actual numbers. Okay, so then compute the mean and the median of the original data set and the trimmed data set. And here what I found is that the mean decreased and the median stayed exactly the same, at least to 3 significant digits after the decimal point. So I'll talk about all this stuff more when I show you the Python code, and I hope you enjoy working through this exercise. Here's where I create the data, pretty simple. Here's where I create a copy of the data. This is often useful. I did basically the same thing in the previous exercise, except there I didn't explicitly create a copy, I just created a new variable. But you often don't want to, let me rephrase that. You often want to preserve the original data. So if you're going to change the data or manipulate the data or drop values from the data, it is often a good idea to make a separate copy, a separate variable that you can change to leave the original data intact. Okay, and then I didn't specify this in the instructions, but I hope you are gaining the habit, you're developing the habit of visualizing data whenever possible, whenever appropriate. So even though no one told you to visualize the data, it's always a good idea to do that. Okay, so here's the histogram of the data values by the counts. And it's pretty interesting to see that it has kind of like a 1/f shape, like a power distribution shape. So less likely to observe values as they get larger, except something's happening here at the end. And basically this is the result of the boundaries of the sine function. So sine function has boundaries between -1 and +1 because the fluctuations go between -1 and +1. So then you pass that through the natural exponential, and you see these are the values that are very close to -1 in the sine function, and these are the values that are close to +1. Okay, and then the natural exponential function also compresses the data values. That's why you see more here than here. All right, so interesting case for data trimming. And let's see, so here is where I do the actual trimming. So here I define a variable k. This is in percent. This is percent of data to remove. But we need to transform that into points because, the percent, the number of data values that you remove is always going to be 4%. But what is 4%? How many data values does that correspond to? Obviously, that depends on the sample size. So with a sample size of 10,000, then 4% corresponds to 400. And because we're doing this two-tailed, it means 200 on either side. So that's what I do here. So this ends up being 2. and then I divide by 200 and multiply by n, and this is going to give me a number of points. But then I'm going to use this as an index, so it has to be an integer, so then I convert it to int. So there's a lot going on in this line. It's pretty condensed, but I hope you see what this is doing. Basically, it's telling us how many data values we need to remove based on the percent of data distribution that I want to remove. Then what I do is sort the data values and then take from this copy of the data index the first 200 and the last 200, and I set those to be NaN. Okay, and then here I'm counting the total data set size, and this is a function you can use to count the total number of data values that are real value, that are actual numbers, not NaNs. So numpy.isNaN will return a Boolean of trues and falses. So it's going to be trues where we have NaNs and falses where we don't have NaNs. And then here I negate it. So that means it's going to be true where there are valid data points, where there are non-NaN values. And then I just sum up all of those. Okay, and this is just a bit of a sanity check. If this were any numbers other than 10,000 and 9,600, then yeah, we would have made, like a coding mistake. I don't know, could have been something like this. Maybe I did this by accident, then we know that there's a mistake here. Okay, so then here I compute the mean and the median. This part is fairly straightforward. It's the mean of the original data and the NaN mean, of course, of the copy data with the data trimmed. Now, we see yet again, just like what we saw in the book chapter in the text, the median does not change at all, and the mean decreases a little bit. Actually, this is less of a decrease than the example I showed in the book. Now, the question is, are you surprised, and why does that happen? The answer is you should not be surprised, and the reason why this happens, let me first talk about the median. Now, remember, the median is the center value of a distribution. So if you're removing data values from the left and the right of a distribution, the median is not going to change at all. The only way that this could possibly change is if you have, if you have an odd number of data points. So then you might end up removing one more data point on the left, for example, compared to on the right of the distribution. But in general, you would not expect the median to change for a two-tailed trimming. Then we have the mean. Now, it is not trivial that the mean would change after two-tailed trimming. It's also not trivial that the mean would decrease after trimming, but that is to be expected given the shape of this distribution. If this were a symmetric distribution, then we would expect the mean to be the same or very, very similar before and after data trimming. But this is an asymmetric distribution. You can see that there are more data values clustered here, so therefore, when we remove data values here and here, we can expect that the mean will decrease because removing large values here has a bigger impact because there's fewer large values compared to removing values here where there are more small valued numbers. As I mentioned at the outset of this video, it's a fair discussion of whether data trimming the way that we've done it is really appropriate for this data set. But nonetheless, my goal here in this exercise was to give you an opportunity to basically just to figure out how to code this statistical procedure, and I hope you found that worth your time. Here we are with exercise 3 of chapter 7. This is a continuation of the code on data trimming. So if you haven't done the previous exercise, you definitely want to do that before continuing on to this exercise. In fact, what I'd like you to do in this exercise is paste the code that you wrote in the previous exercise into a for loop. And the idea is to vary this k parameter. Remember, k is the amount of data that we are trimming. So in the previous exercise, we just fixed it at 4%, 2% from the bottom, 2% from the top. Here, you would vary k from 1% to 50%. So different iterations. In the for loop, you just trim the data, exactly the same data set, but different amounts of trimming. Okay, and then compute and store the mean and median at each iteration. And the reason why we are going to do that is for visualization. So we are going to compare the impact of data trimming on the mean versus the median for different values of k. And I'll show you that in a moment. The one thing you also want to do is print out the data set sizes exactly the same as how you did in the previous exercise, but now you're going to print it out for each value of k. All right, so let's see. Here's the figure. So this is the figure you want to create. What you see here is not the mean and the median values themselves, but the change in the mean and the change in the median from each iteration, so each level of k, each amount of data trimming, relative to the original data set. So this is another reason why you need to keep the original data set and make copies of it to trim. And then I've also converted this into percent change. So this is 5%. So this data value here means that when I trimmed whatever this is, 16% or something, when I trimmed 16% of the data, then the mean decreased from the original data set mean by 5%, while the median decreased by 0%. So it actually didn't change at all. This black line here is pretty boring, but it is also informative. So that's the goal of this exercise. So now I will switch to Python. I'll show you my code solution, and then I'll make a few observations about this graph and what this exercise means. After having gone through the previous exercise, so exercise 2, I believe you will find that this exercise, exercise 3, is not terribly difficult. So it's just copy pasting and writing some extra overhead code to deal with for loops, to store the results, and so on. Now, in the book instructions, I did not specify which values of k to use. I only specified the boundaries of 1 and 50%. So I chose to use to skip in values of 3. So it's going to go 1%, 4%, 7%, 10%, and so on. And there's no particularly compelling reason to skip by 3. You can skip by 1. I just did it for visualization. I thought it looked nice with skipping by 3. Okay, here's where I store the results. You can see that it is the length of k parameters by 2, and that's because we need the mean and the median. Okay, so you will recognize all the code in here. So this code, and this code is exactly the same, literally copied and pasted from the previous exercise. I put it inside a for loop. That part is new. Computing the means and the medians is not really new, although I am converting this to percent change. So that part is new. We didn't do that in the previous exercise. And then printing out the data set size. Notice, by the way, that I'm not creating any new data. In fact, this is the same data set as that I created in the previous exercise. Okay, so then we run all this, and this basically just confirms what we expect to see. So here is the data set size when we remove 1%, when we remove 4%, 7%, 10%, and so on. I guess, if you wanted to make this a little bit richer, you could add removing k% to make that a little bit more clear in here, but whatever. Okay, and then here I'm visualizing the results. This is not terribly complicated code. I'm just plotting the 2 columns from this results matrix. So this is the mean, or the percent change in mean, and the percent change in the median. And that you see here. I guess I don't have too much new to say about this graph, besides what I've already said in the previous video, at the end of the previous video. Basically, the median does not change at all. That is trivially the case because we are trimming from both sides of the distribution. And the mean decreases. Again, it is not trivial that the mean will change, nor is it trivial that the mean will decrease. That is a result of the data distribution. Let me scroll back up to the code from the previous exercise. Here you see the data histogram. So the mean continues to decrease because we're cutting off more extreme values from the right side than we are from the left side, just because the data set is shifted the way that I created these data. Okay, so if you're curious, I encourage you to now use this code for this exercise as starter code to continue exploring. You can see what happens when you trim only from the right side, what happens when you trim only from the left side, and so on. Welcome to exercise 4 of chapter 7. Here we are going to explore outlier removal and its impact on histograms, and in particular, the visual appearance of histograms, also using different rules for generating the number of bins in a histogram. So there's a nice exercise because it really integrates concepts that you have learned about in this chapter and also in previous chapters. Okay, so create a data set of 1,000 random numbers drawn from an F distribution. I haven't yet talked about an F distribution. It's super important for ANOVAs. So you will learn more about F distributions and their shape, their nature, their degrees of freedom, their parameters, their relationship to T distributions, and so on. So you learn more about that later in the chapter on ANOVA. But for now, yeah, you can just look up numpy.random.f to learn how to generate the random data and using 5 and 100 degrees of freedom. Again, these are concepts I will talk more about later. For now, suffice it to say that there are two parameters that you need to supply to create an F distribution, and they are called the numerator and denominator degrees of freedom parameter. So for now, just use 5 and 100. Don't worry about what those numbers mean. You will learn about that later. Okay, so basically an F distribution is positive values only. It's skewed to the right. I will show you the histogram in a moment. So then using the Z-score method, identify and remove outliers defined as having a Z-score greater than 3. Okay, and then you can report the number of data values that were removed. So in this case, with this run that I used to write this text, it was a little under 2% of the data were removed based on this Z-score threshold. So that is the first part of this exercise, just generating these data and removing some outliers or identifying some data points as outliers. Now, you do not want to overwrite the original data set because you're going to want to create histograms of the original data and the cleaned data. That is the point of the next part of this exercise, which involves creating histograms. So what you see here is, actually, let me just focus on this one histogram. So here you see the F distribution, it's positive values only, and it has this pretty strong right skew. Okay, and you see that there are two histograms being plotted here, pre-cleaned and post-cleaned. So this is basically the original data set and the data set after removing any data values that have a Z-score greater than 3. Now, this x-axis here is actually the F value. It's not the Z-score, but it just happened to work out that the Z-score value of 3 roughly corresponded to an F value of somewhere around 3. So you can see that a lot of these points got removed. Okay, and then a couple things I would like to remark. One is that technically, by the letter of the law of statistics, visualization, I shouldn't really be using lines here to connect these different dots. But in my opinion, because I am plotting two histograms on the same plot, I think showing lines makes it a little easier to visualize. So this is another one of these cases where, in my humble opinion, it's okay to bend the rules a little bit in the interest of clarity and visualization. Of course, you're welcome to disagree. I encourage you to explore other visualization methods. You can use bar plots, for example, but I think this visualization looks clear. Anyway, so what you see is that the exact shape of the distribution changes before and after cleaning. So, it's like the exact location that counts at these different F values is different before and after data cleaning. Now, one important interpretation of this is that when you are looking at a histogram and evaluating and interpreting a histogram and the characteristics of the data based on the histogram, you shouldn't look too precisely. So, you have to like squint a little bit to look through your eyelashes, as we say. So don't focus too much on the tiny little details, because even things like changing the rule, this is the Freeman-Diaconis rule, but changing the number of bins that you use will have an impact on the precise details of the histogram shape. So instead you focus on the overall shape. Like, for example, there's one peak towards the left. There's only positive values. The distribution is shifted to the right. These kinds of general statements, observations, qualitative features of the distribution. Okay, and when speaking about the distribution at that level of generality, then we see that the distribution to the left of the cutoff is not really changed, right? It's overall the same. It still has one peak. It still has this rightward shift, but obviously we're missing a lot of data values after we have cleaned the data. So we removed all of these data values. So the distribution shape does change when we removed outliers, but only changed up to a certain point, and lower than that value, it's overall the same. Okay, so this is using the Friedman-Diaconis rule. This is using a fixed number of bins, and here I'm using the same number of bins, or the same bin boundaries for pre-cleaned and post-cleaned. So that's why the squares and the circles overlap perfectly, because the bin boundaries is the same. So, and then you see, well, they don't overlap perfectly down up here. In fact, here for the clean data histogram, they are all exactly 0. These values are exactly 0. There's 0 data points in these bins. So you're going to have to figure out a way to make sure that you're using the same bin boundaries for both the cleaned and the pre-clean, the original data sets. Okay, so I hope that's all clear. Now I will switch to Python and show you my code solution. So the first part of this exercise is not very difficult to do, especially after you've gone through the previous several exercises. So here I create a data set comprising numbers randomly drawn from an F distribution. You can see here are the two key degrees of freedom parameters for a F distribution. Here I z-score the data, and you can see I'm storing this as a different variable in Python, so I'm not going to overwrite this variable x. Okay, and then here I clean the data. I basically create yet another variable here, where I take all of the data points from the original data set, where the z-transform data are less than the threshold. So it's not a lot of lines of code, but it can be potentially confusing because I'm using 3 different variables here. So x is the original data, xz is the z-scored data, and then xclean is actually a smaller data set with the data values removed. Remember, I've discussed in the book chapter, and you also saw in the previous couple of exercises, that sometimes it's better not to actually remove any data values, but instead to replace the outliers with the value of NaN. But in this case, I am actually literally removing them. So the size of the cleaned data is less than, it's smaller than the size of the original data. And that's what you see here. So in this case, there was 1.4% of the distribution was removed. And what was it in the book? I think it was 1.7%. It will always be somewhere around 1.5 to 2%. Okay, so here I'm creating the histogram. We have the histograms for the original data and the cleaned data. Now, using the Friedman-Diaconis rule, the code is pretty straightforward here, because I'm computing the histograms separately, independently for each of these 2 data sets, the original data and the clean data. It's a little bit more involved for having a fixed number of bins using exactly the same bin boundaries for both data sets. And the way that I chose to do this is by first defining a variable that I call edges. These are the boundaries, the edges of the 40 bins. Now, if you want to have 40 bins, you need to have 41 boundaries, of course, because all the bins share boundaries except for the outermost bins. So we need 41 numbers to create 40 bins. Okay, and here I'm hard coding this. Probably, honestly, would be a little bit better if I would soft code the number of bins. I could have a variable that says n bins equals 40, and then here this would be n bins plus 1. But anyway, this is how I did it here. Okay, and so now the bin boundaries are based on the original data. So the smallest data value to the largest data value. And then I'm going to apply exactly these same boundaries or edges to both data sets, to the original data set and to the cleaned data set. So I hope that makes sense. Basically, I'm defining the bin boundaries based on the original data, and then I'm applying those same boundaries to the cleaned data, which is a different data set that has fewer data values and a more restricted range. Okay, and from there, I think plotting, this looks like a lot of text, but it's actually not so bad. Just extracting the X and Y values from these variables, and then, yeah, some, labels and setting the marker size and so on. So not super complicated. Okay, let's see what we can see here. Yeah, so again, you see that the overall shape of the distribution is the same. The exact features of the distribution, the exact locations of the bin centers on the x-axis and the exact heights are different. It is not surprising. These are different data sets with different sizes and different numbers in them. Of course, a lot of the numbers overlap, but we're missing a lot of data here in the clean data set. And here, yeah, again, as I mentioned before, there's the same number of data points in this bin in both the pre-cleaned and post-cleaned data data sets. It's really only up here where we see a change where all of these values for the cleaned data set are exactly 0. Those data have been removed. There are no data points at, between a value of 3 and 3.1. So I hope you enjoyed working through this exercise. I think the important take-home message here is that anytime you change something about the data, that's going to change at least the granular numerical details of the histogram and the distribution, but the general overall qualitative shape of the distribution is not going to be hugely impacted by data cleaning. This video corresponds to exercise 5 of chapter 7. Here we are going to use our skills of data cleaning and outlier detection and removal and looking at descriptive statistics of a data set in real data, using real data that are freely available online. Let me give you a fair warning. This exercise relies on knowledge of pandas and seaborn. So if you are very familiar with those data sets, then it shouldn't be a problem. If you're not very familiar with those data sets, then you might find the coding aspects of this exercise and the next exercise to be challenging, even if you understand all these statistics concepts. So if you're really struggling just with, organizing the data in pandas and visualizing with seaborn, feel free to just look at my code online and copy and paste the non-statistics related code, which is basically just importing and working with the data, so you can focus more on these statistics concepts. Okay, so let's see. Here is the link to the data set. You can also just copy this from my code on my GitHub site. So import the data directly from this website from UCI, University of California at Irvine, and then put it into a pandas data frame. Here you can see what the data set looks like. So this is the first 5 rows of data. There's lots and lots of data. This is just the first 5 rows. You can see, yeah, there's a bunch of variables: age, sex, height, weight, and then a bunch of variables that are related to EKG, or electrical monitoring of the heart rate. So QRS refers to different characteristics of the waveform cycle. So once you import these data, you're going to want to make a copy of that data frame. So therefore, you can identify outliers and mark them for removal by replacing them with NANs, for example, in one copy of the data, and you still have access to the original copy of the data. That's important for this and the next exercises. Okay, so then use Seaborn to create box plots of the data that will look like this. So here you see the raw data, and here you see the Z transform data. So first of all, it's pretty interesting that even in real published data, you see lots of outliers. This is normal. Outliers are not some weird thing that happens only with crappy data. If you have outliers in your data, it doesn't mean you're a failure, that you didn't collect good enough data. Real published data still has lots of outliers. In fact, data scientists spend a lot of time cleaning and preparing data for analyses, and relatively little time actually analyzing the data. So this is just how it works with real data. Okay, but one thing I would like to um, illustrate to you and impart this idea on you that all of these different variables have their own scale. They're all in different scales, and so it's really hard to come up with one threshold, or I should say, it's inappropriate to have one numerical threshold for identifying outliers for each of these variables. For example, if we look at height, what are the outliers here? I mean, these two look like outliers. These are really tall people. Maybe these are, these might be data coding errors or something. But where do we set the threshold for identifying outliers in height data? Do we set it at 500 or maybe 237? It's pretty arbitrary. And that exact, let's say we set it here, we set it to 237. Now that exact value is going to remove all of the data from Qt variable. So, that is completely inappropriate. We would need to come up with new or distinct thresholds for identifying outliers in every single variable. You would need to have a lot of domain knowledge to do that. And it's subjective. I mean, every cardiologist would come up with different numbers for thresholding these different values. Okay, so that's when we're working with the raw data. Here you see the Z transform data in this lower plot. And now you see all of the data values are normalized. They're all standardized. So now it's much easier. We can say, well, any data value that is greater than 3, for example, we consider an outlier. Or maybe 5. We want to be a little bit more inclusive and not remove so much data. So there is still some aspect of arbitrariness and subjectivity with picking this threshold, but at least, we pick one threshold and we apply it equally to all the data variables. So we've removed, a lot of subjectivity here with only one point of subjectivity, which is the Z value to use to remove data. So generating this graph is basically the goal of this exercise. One thing I forgot to mention is sex is a binary variable, so it's 0 or 1. So you do not need to Z transform this. There are not going to be outliers in this variable, and we can directly interpret these numerical values. We don't need to worry about Z transforming them. So transform all the other variables and then make this box plot using Seaborn. So here is code for importing the data. Again, feel free to just copy and paste my code here. This is not important statistics code here. And then the names of the variables, I'm only using the first 9. The names of these variables, basically, I just got from this URL here, so you can go check out that website if you like. Okay, so we import the data directly from the web, and here I'm just printing out the first couple of rows here using df dataframe.head, this function. Okay, so now I'm going to create a box plot of the raw data. It's actually fairly straightforward. In Seaborn, it's just the function box plot. You specify the data frame to use, and here I'm just setting the X and Y axis labels. Okay, so that's this. And then for the Z scoring. So now I create a copy of the data frame. I call this df_z for Z transform data frame. And here I'm looping through all of the columns and then computing the Z score. So I say the data at that column minus the mean of that column divided by the standard deviation of that column. And then this is just to skip the column called sex. So if the column has the title sex, then we skip that variable. We do not want to Z transform that variable. Of course, you actually could Z transform sex column as well. It's not going to be negative. It's not going to have any impact. But I added this little bit to the exercise to give you more practice working with data frames and applying transformations only to specific columns of data frames. Okay, so then here we see the data frame again, and then we do the visualization here of this box plot. Okay, so those are the two box plots that you see in the figure. This code here is nothing new. It's actually just combining the two box plots into one figure. And then this is the figure that I used in the book, in the text. Now for exercise 6 of chapter 7. This exercise follows from the previous exercise using the same data that we imported in exercise 5. So you definitely need to have gone through exercise 5 before working on this one. So in the previous exercise, we imported the data and we Z transformed. And we didn't do anything else. We didn't remove any outliers. That is the goal of this exercise, exercise 6. So what you want to do here is identify and remove outliers based on a Z-score threshold of 3.09. Now that may seem like some weird arbitrary number, but it actually is not so arbitrary. It corresponds to a probability or a p-value of 0.001. You will learn more about that in a later chapter, the chapter on probability theory and also the chapter on hypothesis testing. But for now, you can just use a value of 3.09. So make a copy of the raw data or use the copy of the raw data that you already have. Any data value within each column that has a Z-score exceeding this threshold here, set that data value to NaN. And we want to do that because we're going to visualize and also inspect the means of the data before and after removing data for because they are outliers. Okay, so then you want to create a couple of bar plots. One of them you can see here, this pair of bar plots. Now this is all the raw data. Let me shrink this a little bit. This is all the raw data. We are not visualizing the Z transform, the standardized data. We are just visualizing the raw data. But this is the original raw data, exactly how we pulled it off the website. And this is the cleaned data. So you can see that there are outliers removed. These two outliers are removed here. This outlier here, this small value here, was removed over here and so on. And also, yeah, this one was removed up here as well. So we still have the raw data, but now we have removed data values based on, not based on the raw data values, but based on these Z transformed data values, these standardized values that you computed in the previous exercise. Okay, so then this is one part. Then there's a little bit more I want you to do for this exercise, and that is to compute and print the means of the raw and the cleaned data features and print out the results here. So this column here is the original means, and this column is the cleaned data set means. So you can see some of them are the same, right? So age is exactly the same. And what does that mean? That means that there were no outliers in the age data variable. So no data points were removed for being excessively large or small in the age category. Same thing with sex, but now we get to height and we see that the height has decreased. This tells us that there were some outliers in height and they were large outliers. So we did a two-tailed outlier removal. So the mean could actually increase, and that you see here with weight. Actually, the average weight went up a little bit. So if you use a Z-score threshold of 3.09, you should be able to reproduce exactly all of these numbers. Of course, I encourage you to explore trying out different thresholds. You can try a one-tailed threshold, but then obviously, these numbers might change. Okay, almost done with this exercise. There's one more thing I want you to do, which is basically to visualize these. Sorry, let me scroll back up here. So visualize these results in terms of the change in the mean before and after data cleaning. So here we see that the numerical values range quite a bit, right? We go from 0.5 to 367. So the numerical range of these values is quite different across the different variables. So what I want you to do is now compute the change in the mean in terms of percentage change from this value to this value. So post-cleaning relative to pre-cleaning, and that you can visualize here. And basically what I want to highlight here is that in real data sets, when you clean the data, you apply a Z-score cleaning threshold or any other kind of cleaning mechanism, you can find that the means will sometimes decrease and sometimes increase. So it's not trivial like in earlier exercises that the mean will always decrease after removing outliers. It really depends on the nature and the sign of those outliers. Okay, so quite a lot of things to do in this exercise, but I hope you enjoy working through them. I think this is a really great exercise for gaining a real applicable skill, working with real data and cleaning and visualization and the Pandas and Seaborn libraries. So here I am soft coding the Z-score threshold. Again, if you use 3.09, you will be able to reproduce exactly my results. There's no random stuff going on in this exercise. But yeah, I encourage you to try different thresholds as well. Okay, so now I create a copy of this data frame. And here you can see I'm removing, or actually not removing, I'm replacing data values with NaN if they are greater than the threshold or less than minus the threshold. This is a subtle but really important point because it's so easy to make a mistake like this. This is a very easy typo to make in code, and you're not going to get an error because there's nothing wrong with the code here. But what are we doing here? We're basically, actually the effect here is to remove all of the data, right? Because here we are removing any data values that are less than the positive threshold, but we want to remove data values that are less than the negative of this threshold. So just something to be mindful of when you're working with real data. Okay, so then, yeah, I think creating these box plots is not so difficult. In fact, you can literally copy and paste the code from the previous exercise. All you need to do is make sure you are using the correct variables. So the raw data, the original data, and the cleaned data here. So yeah, as I showed in the text, you can see that the data now retain their original numerical ranges, their scales, but the data value, the outliers have been removed. Now you can also see that the y-axes are different here. So the y-axis is much, much larger here because it needs to account for these large values here. So if you like, you can also change the x-axis limits so that they are the same for these two panels. But that's just a little bit of an additional thing if you would like to do that. Okay, and here I am computing and printing the means. So I have the means of the original data, the means of the cleaned data, and now these data, so the df underscore clean has NaN values in it, right? Because up here I replaced these large values, these extreme values, which I'm calling outliers, I replaced those with NaNs. Now, you know from previous videos in this chapter and earlier chapters that in NumPy, the mean will be NaN if at least one data value is NaN. So with NumPy, you need to use a special function, which is NaN mean. But in Pandas, you actually don't need to do that. So Pandas function mean, or this method, mean will automatically exclude NaN values. It's a little confusing to remember, but that's how Pandas works. Okay, and then, so actually this is going to return a data series. We just want the data values. So that's why I'm using this additional method .values. That's going to ensure that these variables here is literally just the values of the means and not a whole additional data series, which we don't need. Okay, so then, yeah, I'm just kind of zipping up the column names and the mean values and then printing them out. So this is pretty straightforward. This just reproduces the text that I showed in the book. Okay, and then here's where I compute the percent change. Again, percent change is straightforward to compute in terms of the formula. You just have to make sure you're thinking correctly about which variable gets subtracted from what and which variable goes in the denominator. And basically, it's whatever is the change from is what gets the minus sign, it goes in the denominator, and the numbers that it's changing to is only in the numerator, and that is a positive value. Okay, and now this expression on its own gives us proportion, and then here we are multiplying by 100 to give percent. Okay, and then after that, this is just some pretty straightforward plotting. Yeah, so what you see is that some variables are getting smaller. The mean of some variables decreases after cleaning, and some variables it increases. Sometimes it increases a lot. Sometimes it only increases a tiny bit. But yeah, I think These kinds of visualizations are really useful to look at in real data to get a better understanding of the quality of the data and also the nature of the data before and after cleaning.